In an unfortunate series of events, the science department and a good portion of the building flooded yesterday. But when we're talking about the building being in water, it's strangely appropriate that we would talk about acids and bases in water. And those are dissociating, and that's the whole idea of being aqueous. All right? So what we need to address is the idea of how these different acids and bases interact with water. And the idea for now, for Arrhenius and Bronsted-Lowry anyway, that acids have to do with H pluses, which are protons and become H3O plus, and bases have to do with OHs, right? So let's take a look at an aqueous dissociation. You put an acid in water, and we'll use a generic acid. We'll just call it HA. So some generic acid. When you put that HA in water, those waters kind of complex out the hydrogens, right? There's this polarity interaction. And that's not perfect terminology, but it'll do. We've got our equilibrium system. Acids donate protons, and bases accept protons. And yes, I'm pointing at H2O as a base, and that's material for a whole different video. But this is going to have to donate a proton to give an H plus up, and we'll end up with H3O plus, all right? The hydronium ion. And what's left of our HA is just the A minus. And there's several things I want to do with this before we look at the bases or anything else. I want to look at a few ideas. First up, HA turns into A minus by donating a proton. That is the basic definition of something that is an acid. All right? H2O turns into H3O plus by accepting a proton. That's our definition of a base. All right? Things that accept protons. And that's going in that direction. But in an equilibrium system, the reaction's actually going in both directions, and it's kind of a tug of war, as we look at in the equilibrium videos. So now I want to stand here and look at the reaction in that direction. And I think that's a very useful tool, is looking at it the other way, because we're used to reading left to right, but if I'm standing over here, it's natural to read that way. All right, so in the other direction, what is happening? H3O plus donates a proton, and it becomes H2O. And what do we call things that donate protons? Well, that's an acid. And when it's on this side, we call it a conjugate acid. And we'll write that definition down in a little bit. I'll abbreviate it from here out with just Ca, because that's a bunch of writing. And then A minus, we need to look at what it does in that direction. Well, A minus turns into HA, and it does that by accepting a proton. Things that accept protons we call bases. And when it's on this side, we're going to call it a conjugate base. Okay. Now, I want to define those terms, and then we'll take care of business with what I'm going to write there. And then maybe we can take a look at some aqueous base dissociations. So, first up, to define our conjugate acid. It's an acid, right? But it's an acid that formed when a base accepted a proton. This came from here, this was a base, it accepted a proton, and it became an acid. And I think in the big picture it kind of makes sense, because H2O gained a proton, right? So now it has a proton that it can give away, okay? So H2O was a base, it's also an acid, but H2O was a base, it gained a proton, the new thing has a proton that it can give away, that means the new thing must be an acid. So our conjugate acid is the acid formed when a base gains a proton. All right? The acid formed when a base gains a proton. So that's our conjugate acid. Our conjugate base, and I'll abbreviate that similarly, CB, is what is formed from our acid. HA was an acid. It donated a proton, because that's what acids do, and became A minus. Now A minus is missing a proton, and so it is in a position to accept a proton. And going in this direction, it can do so, and we get HA. So this is in a position to accept a proton. That means it is a base, right? In that direction, it accepts a proton. That's our conjugate base. This is not the best color choice for this, but we'll live. All right, that is our base that's formed when an acid loses a proton. And again, it makes sense. If an acid loses a proton, there is space in its life to gain a proton. So in the other direction, it can gain that proton, and things that gain protons we call bases. I want to sneak in right here something that I write for every single equilibrium problem, and that is a dissociation equation. And if you look at some of the other videos about equilibrium and such, it's a huge deal, okay? And it's a quantitative way that we can assess the strength of acids and bases. So we're going to write an aqueous equilibrium constant, an acid dissociation constant for this generic acid. And if you look at the equilibrium videos, I know I refer to those repeatedly, this is based on Goldberg and Bogg and their law of mass action, which is an idea relating the amount of reactants and the amount of products at equilibrium. And so we just take our product concentrations to their coefficient powers, which in this case for acid bases ends up being 1. And then we're going to divide by our reactant species to their coefficient powers. And you'll notice I didn't write H2O. H2O is a liquid, it's a pure substance, it doesn't have a concentration, so it's not affecting our equilibrium. Other ways that you wouldn't see it is if you had a solid here, that's not part of our equilibrium system, so we would ignore it. Gases are a different scenario, but they do come into play in equilibrium systems. It's not going to be an issue for our acid-base problems. So in short, this is a huge deal. This and this are aqueous species for our numerator, this for our denominator, and we're not including the H2O because that's a liquid, that's a pure substance. And I'll say that again in slow-mo. Every time you're writing an aqueous dissociation equation for an acid or base, water is not going to show up here. It's a liquid, it's a pure substance. That's like the most common question, so we need to address that right now. Okay? I'm going to erase this. We'll write a generic base dissociation equation, and then we'll talk a little bit about this terminology, which is a bit of review, and maybe look at some examples. So let's make some room to make it happen. For our base example, let's look at some generic base. B. All right? Now, that's not boron, and it's kind of a flaw in my whole system here, but I'm just going to call it base B. It's not boron, that's generic base B. And we know that bases are things that accept protons, and this is an aqueous dissociation, it's in water, so every single one of these is going to look like this. Something, some base plus water. Now in this case, bases accept protons. Water is going to have to donate it, so water now becomes our acid. And when this base gains a proton, we get BH+, right? So base accepts proton, becomes BH+, and then water loses a proton, so it becomes OH-. And you can kind of see this Arrhenius definition and even the Bronsted-Lowry definitions here. While we're writing things, let's get our K expression right away. This is not a Ka, it's no longer an acid, it's not a Ka, it's no longer an acid dissociation equation, it's a Kb, a base dissociation. But the process is the same, products over reactants to their coefficient powers, and we're only going to do that for aqueous and gas, but not gas for acids and bases. So we're going to have our concentration of BH+, concentration of OH-, over the concentration of B, whatever that is. All right? And we can label some things the same way we labeled conjugates before. This accepts a proton. As we are reading the equation in this direction, this turns into this, and it does it by gaining a proton. Things that do that we call bases. All right? This, going in that direction, turns into OH- because it donates a proton, and things that donate protons we call acids. All right? H2O becomes OH- by losing an H, donating a proton. That's what an acid is. So that's what things are in this direction. As we look at things in this direction, how do they change? Well, OH- turns into H2O. It has to gain an H. It has to accept a proton. And things that accept protons we call bases. And when it's on this side, we're going to call it a conjugate base. And then reading this in the other direction, BH+ turns into B, and it does that by donating a proton, by losing a proton, right? This doesn't have that proton over there. Things that donate protons we call acids, right? And when it's on this side, we're going to call it a conjugate acid. Now, strength and things, I guess we'll address that here in a minute. Common question, like, how do we know if it's the conjugate? Short answer for that is if it's appearing on the product side, that's what we'll call our conjugate. All right. We have conjugate acid-base pairs and all that, but for writing these things out, if it's on the product side, those are our conjugates. And I'll say that again in slow-mo. Conjugates, product side. That's how we know which ones they are. And then liquid, not appearing in our equilibrium expression. There's going to be a rather important note that I will write at the bottom, and that is that strong acids and bases are strong electrolytes, and they have weak conjugates. Strong acids and bases have weak conjugates. Right? So a strong acid would have a weak conjugate base, and a strong base would have a weak conjugate acid. Right? In fact, they're essentially neutral. And I'll write that strong acid gives you a weak conjugate base, and a strong base gives you a weak conjugate acid. And what I'm not going to say is the reverse scenario. All right? So a strong base, same deal, weak conjugate acid. All right? And I'm going to sneak in over here that these things here are essentially neutral. All right, they're so weak that they give you a pretty much neutral solution. And that's going to come into play when we're talking about the acid-base nature of salts. So for right now, strong begets weak. And what isn't necessarily true is that weak begets strong. In fact, weak usually gives weak almost all the time. It's a statistical game. There's a ton of weak acids and bases. There's very few common strong acids and bases. So the odds are if you have something weak, it's not going to give you a strong conjugate. It's going to give you a weak conjugate. And they didn't really budget space well for that. So I'll just sneak it in right here. Fine print. Weak acids and bases almost always have weak conjugates. All right, so weak acids and bases, almost always weak conjugates. And again, it's just a matter of statistics. I want to make sure we're okay on time for this video. Let's take a little more of a look at the idea of strong electrolytes and weak electrolytes and why the K expression matters. And then, depending on time, we'll take a look at some examples of aqueous dissociations. So let's talk electrolytes, and this is something that comes up in other videos, but we'll take care of it right now. Electrolytes, if you've seen the movie Idiocracy, electrolytes are what plants crave. But electrolytes are things that dissociate, right? These dissociate in aqueous solution. You've probably also heard of electrolytes because it was like a big Gatorade marketing thing for a while, right? And when we talk about, again, this idea of electrolytes, why are they called that? Well, when they dissociate, to dissociate is to separate into ions. And those ions allow the solution to carry a charge, right? They allow the solution to carry charge. And when we're talking about charge being carried, moving charges, we're talking about conducting electricity, hence the name electrolytes. And I don't have time in this video to mention it, but H2O, covalent compound, a molecule, no good way to carry charge, and it does not conduct electricity. And I'll say that again because that's not something that people usually know. H2O water by itself does not conduct electricity. When you get tap water, it's got a bunch of other ions in it, right? And those ions can move around and allow it to conduct electricity. So, something to take note of. Pure water doesn't conduct electricity. Covalent compound, no good way to carry charge. when you put some ions in there, they can carry charge, and you get electrolytes, right? They can conduct electricity. Now, electrolytes are broken down into two main categories. We can have strong electrolytes and we can have weak electrolytes. And there's quantitative and qualitative ways to look at this. So qualitatively, we'll say that strong electrolytes dissociate completely. All right? Now, that's not technically true because you can't have zero in an equilibrium system, but for practical purposes of math, it's true enough, so that's okay. So qualitatively, we can identify it that way, and quantitatively, we can, we can look at this in terms of Ka. They have a large K values. These are our equilibrium constants. And so the most common question is, like, how do I know what's large? And the answer is literally the word large, or the word very large, all right? Practically speaking, it depends on who you talk to in terms of numbers, but we can agree, like, I think HCl off the top of my head has a K value of like 10 to the 7th. That's a big number. That's a large K value, all right? But on tables, how will you know if it's strong? Looking at a Ka table or a Kb table, it says the word large. It's not a number. They say large, okay? And that implies that it's going to dissociate completely. So if we've got strong electrolytes, we also need to look at weak electrolytes. And weak electrolytes, I mean, we can look right here and say qualitatively, they don't dissociate completely, right? They do not dissociate completely. And then the important part for us in the long term is what is true quantitatively. The fact that they have not large K values. So the K values are not large. All right? In fact, like, they'll be numbers, okay? So they will actually have numbers. And those actual number values are going to be between 0 and 1. And what that means fundamentally is that proportionally, at equilibrium, we're going to have more reactant than product, all right? And again, that's not an intuitive idea, the idea that all reactants don't turn into products necessarily. In fact, if you have a weak electrolyte, most of it doesn't. So an example of a strong electrolyte might be something like table salt, sodium chloride. There is no NaCl in salt water because that NaCl dissociates to produce sodium ions and chloride ions. When you have something like, say, calcium carbonate, limestone, that's not a strong electrolyte. It doesn't dissociate all the way. And so you may actually have some calcium carbonate, or at least you'll have solid calcium carbonate precipitate. Now, why do we care about these words with strong electrolytes and weak electrolytes? Because acids and bases are electrolytes. In fact, all strong acids and bases are strong electrolytes, and all weak acids and bases are weak electrolytes. So all strong acids and bases are strong electrolytes. And then all weak acids and bases are weak electrolytes. And for acids and bases, we don't just have generic Ks, we have Kas and Kbs. And you saw that when I was writing the Ka expression and the Kb expression earlier for those dissociation equations. But Ka is our acid dissociation constant. All right? And Kb is our base dissociation constant. And what is important to us, the idea that larger values are stronger, all right? Larger K values give us stronger electrolytes. So a skill you might need in general application is like compare the strengths of these acids and bases. So you would look up the Ka or Kb values in a table. The higher the value, the stronger it is. The lower the value, the weaker it is. And I think for this video, it's already been long enough. It would be nice if we could sneak some examples in, but I guess we'll have to do that in the next video.